There we go. Energy. This word triggers many thoughts in us. Green energy, blue energy, bad energy, energy consumption, and energy bills. Some of you might be thinking right now, did I remember to turn off my lights at home? And here in this town, I think we could turn off some lights. The topic touches all of us. It's a lifeline for individuals, and it's absolutely crucial for businesses. And the way we produce and consume energy has a huge impact on our planet. Imagine this, 80% of all greenhouse gas emissions globally are accounted to energy-related emissions. So that's a significant number. CO2 emissions have set the world on course for a rise of 2.4 degrees in global temperatures. This is way above the Paris Agreement goal that limits global warming to 1.5 degrees. The World Energy Outlook report from just now, October 2024, underlines the inseparable links between energy and climate change. I do have some good news, though. The recent scenarios state that the demand, or the growth in energy demand, is slowing down. And this is due to energy gains, electrification, and the rapid growth of renewables. But these kinds of scenarios, they only really take place if we here all do our part. So let's get to work. My name is Maja Andersson. I'm a senior practice manager at AWS Professional Services for automotive and manufacturing. And today I have the joy to have two of our AWS customers, Jon Dijserod, CIO from Volkswagen Poznan, and Marco Caserta, a senior applied scientist from Amazon, with me here today. They will soon be sharing how it was possible for them to reduce energy consumption and hereby CO2 emissions and energy costs in their companies. And they will explain how they leveraged machine learning on AWS to do so. But you may be thinking that, well, why are we, or who are we at Amazon Web Services to talk about energy and talk about sustainability? Well, let me show you how and why this is relevant for us. One of our leadership principles, these are the guidelines at Amazon we use, states that success and scale bring broad responsibility. It means that when we gain impact, it becomes more and more crucial that we don't just take responsibility for our own footprint on this planet, but we realize that we also have a responsibility to function as an example for others. So Amazon's most recent sustainability report from 2023 takes us through some actions that Amazon does to lead the way in sustainability. 100% of the electricity consumption at Amazon are matched by renewable energy. This covers the AWS data centers that your workloads are running on and where your data is stored. But also, it covers the entire operations of Amazon. So we are #1 corporate purchaser of renewable energy. And to ensure our needs, we actually have spun up over 500 energy or renewable energy projects of our own. So these are wind parks, solar farms, and so on around the world. We have actually reduced 3% of our absolute carbon footprint alone during 2023. We are also working on other sustainability initiatives, like becoming water positive. This means that we return more clean water into communities than what we are using. We have reached 41% of this target, and we are on track to reach this water stewardship goal by 2030. AWS Web Services is carrying to these progressive numbers from Amazon through energy efficiency. Now listen to this. A 2024 Accenture study shows that running workloads on AWS is up to 4 times more energy efficient than on premises. And optimized workloads on AWS can lower the related carbon footprint by up to 99%. So this is possible because AWS is continuously innovating to improve our chips, our services, and our infrastructure best practices. This makes cloud, no doubt, the most sustainable and efficient way to run your workloads. Now, what about taking that broad responsibility even further? Kara Hurst, Amazon's Chief Sustainability Officer, states that to drive change, we need to bring entire industries along with us. We need to support other industries in becoming more sustainable, and we can do this, for example, by offering solutions to lowering their CO2 emissions with energy efficiency. Machine learning helps companies become more energy efficient in several ways. It is used for optimizing manufacturing and production processes, and for assets and equipment, it enables predictive maintenance. With machine learning, we can detect anomalies, similarities, or even just patterns. And with this knowledge, we can do proactive adjustments on shop floor and in our operations. And this helps us avoid that costly, unplanned downtime and wasteful use of energy. Also, we can improve the efficiency of our staff by offering them accurate and easy-to-use search services. Today, you will learn about 2 machine learning use cases on AWS. First, how Volkswagen reduces energy consumption of their air compressors in the Poznan factory of Volkswagen, and how Amazon optimizes the energy needed for their heating, ventilation, and air conditioning in the facilities of Amazon Retail. Our first example today comes from Volkswagen Poznan. But first, let me introduce the Volkswagen Group to you. Volkswagen Group consists of 13 different brands, and their manufacturing operations stretch to over 114 factories around the world. More than 680,000 employees work in 150 countries for this OEM that produced 9.2 million cars last year. That is 250,000 cars every week. Their annual revenue reaches over $320 billion. For more than 60 years, Volkswagen has been building cars. And today, software and data are key differentiators in their business. Also, smart solutions enable Volkswagen to run more sustainable operations in their production sites. Machine learning simulations on AWS are driving Volkswagen's sustainability goals. They do this by reducing energy consumption in the Poznan factory in Poland. Let's hear how from the customer himself. Welcome, Jörn Dijsselrode, CIO of Volkswagen Poznan.
Okay, so back in 2019, our both companies started a cooperation, and we call it the DPP, the Digital Production Platform. Today, the DPP combines data from most of our Volkswagen plants around the world. It provides both technology as well as processes for our production and logistics use cases. In fact, we have about 150 use cases live on this platform today, and we're still growing. One of these use cases aims at reducing energy consumption in our plant in Poznan, Poland, and that's what I'll be talking about today. I will show you how this use case is based on our cooperation and how it contributes to maintaining a livable planet by reducing and decarbonizing energy use. Being a mobility company, sustainability is always at the heart of our actions. So we have a clear go to zero strategy at Volkswagen. We strive for a CO2 neutral production in 2040. And we have acknowledged, or we have established 4 major fields of actions to reach our goals. Number 1, we have established an effective environmental management system that measures and steers all our activities. We are protecting the climate by actively reducing emissions such as CO2, and this is actually where we agreed on our 2040 goal. We save resources. Obviously, being an industry company, that's a very important part of what we do. For instance, we're just now working on reducing water consumption per car. We're working on cutting water consumption in half. Last but not least, we're actively preserving ecosystems on our premises, and we are actually controlling how this works and if it works. I brought some examples of what we do, some visible examples of what we do, and they go all the way from big electric trucks down to little bees. So what you see here is a truck. It's a truck that we don't produce in Poznan, but it's a truck that we use for our internal transport. They commute between our sites. We have 4 sites around town, and this is where we use these trucks. This is number 1. We actually are just putting in place number 2 and number 3, and each of these saves about 50 tons of CO2 per year. It's green, so it has a special name that we use in Poznan. We call it the żaba, which is the Polish word for frog. The home of the bees is our 13 megawatt solar park. 25,000 solar panels on 55 acres. This is the biggest on-premise solar PV farm in all of Poland, and we're really, really proud of it. On a sunny day, actually, we can run 100% of the electricity usage of our Września plant just in this solar park. It's a great thing. We all love it, and by now, even the controllers love it. So I think what you can see is that we're working hard on reducing the impact of our actions onto nature and environment. But there's a very basic truth that we did not forget doing all this. Optimizing, compensating, reducing emissions, and so on are absolutely necessary, and they're part of our job. We do it every day. But in the end, the real deal is avoiding the need to consume. It's avoiding the demand even for electricity. Everything we manage to avoid, we don't need to compensate, and we don't even need to pay. In the end, it's a win-win, both for the environment as well as for the economics of our work, and it's just a no-brainer. You see the writing here, the most climate-friendly kilowatt hour is the one you don't use. With this in mind, we went into our plants, we looked at our machinery, went into the biggest consumers of electric energy, looking for ways to optimize. And we found compressed air. Compressed air is needed throughout almost all of our plants. Many mechanical appliances run on compressed air, like might be anywhere from small drills that you have in your hand up to full production lines. In our foundry plant, more than 20% of total electricity of the Volkswagen Poznan foundry run just for generating compressed air. The air is distributed by a pipe system through all our plants, not plants, and it's generated in one central compressor room. Think about one big room, maybe about the size of a basketball field, and it has garage-sized big machines on it that compress the air. Obviously, it takes a lot of room, it's very noisy, and it takes a lot of energy to run these. In fact, if we would build a plant today, we would probably not opt for compressed air in most of the use cases. But as we have running plants around the world today, we have to come up with good solutions to optimize our operations here. What you can see here in the middle is some of the products we manufacture in this foundry plant in Poznan. We manufacture die casting parts, and we have actually produced more than 100 million die casting parts in the past 25 years in this plant. These parts are solid metal parts, such as cylinder heads or axle carriers. We have been producing them virtually for all our brands in the group, so chances are that if you have a Rabbit or a Porsche or a Bentley, there's parts from Poznan in your car. because all these brands are part of our big Volkswagen family. In this foundry plant, we work with 70 production lines, 70 different production lines. Each of these lines is supplied by individual suppliers, so that they don't have the same technology, and they run on customer demand. The compressed air that we need to run these lines is generated by 4 compressors at the moment. And these 4 compressors are run by one specialist. This one specialist actually has to have quite some experience. Listening or hearing that he has to run 4 compressors doesn't sound too complex, but I want to give you a little glimpse into that it is quite a complex task to set up these compressors. So let's do some little bit of mathematics. I just told you we have 70 production lines. Saying, and this is a little bit of a simplification, that each of these production lines can either be running or not running based on customer needs. That gives us 2 to the power of 70 different combinations of running our production. And this actually changes every day. If you try to find that number, I have to read this. It's 1.18 sextillion, a number with 18 zeros. I never heard of it. And this changes every day. It's nothing that we only do seldomly. So what's the specialist have to do then? He can only run the air suppliers. The specialist has 4 compressors. And for the sake of simplicity, let's say the compressors can either be turned on or idle or off. So 3 options. That gives him 3 to the power of 4 options, 81 options to running the compressors at any point in time. Obviously, I did a little bit of simplification there. So if you put this maybe on the background of time, things change, you have unexpected things happening. I think you can see it's a very, very complex decision-making that the specialist has to do. Wrapping it up, what he has to do is he has to find the optimal compressor sequence. Whoops, sorry. I can't go back. There we go. So what the specialist actually has to do in the end is he has to find the optimal setting for the compressors to produce the exact right amount of air for an unbelievably high variety of production possibilities. And he has to do so by minimizing the loss of air and thus energy. So when we did our solution, we started to gather all kinds of data that we could get. We started with historical data, we used the production schedule, and a number of sensor data. Looking into sensor data, the most important sensor data is things like air and electricity consumption, temperature, dew point, airflow, air pressure. This is the kind of data we used. Our solution has 3 process steps, main process steps. The first one is that we predict the future air consumption based on the production program. Number 2 is we then derive a compressor sequence for this production program. And we now still have the 3rd step, which is a manual step. We manually put the outcome of our models into the compressor software. Let's go a little bit into detail. We're working in shifts, working in 3 shifts. And for each shift, based on customer demand, we know which machine is running and which machine is not running. Based on this program, our model predicts discrete air consumption, and the model is capable of doing so in 1-minute intervals. This step actually has the highest complexity as it's predicting a very dynamic system. The underlying model is retrained upon demand. So whenever something changes in the full system behavior, this might be due to outer conditions, such as the weather, as well as to when the system gets bad, you have system changes in terms of maintenance on the system. During production, the model is used whenever we update the production program. So usually this can be daily, but it's not more than 2 or 3 times per week, or it's not less than 2 or 3 times per week. Based on this predicted consumption sequence, we derive a compressor steering sequence for all 4 compressors, and we consider the individual compressors for this. We use a rule-based model for this, as the nature of this problem is more to a deterministic nature. Some older compressors can only be turned on and off, as I showed you earlier, or have maybe an idle status. Some newer compressors have more sophisticated ways of setting them up. For instance, you can put them into a status that says, let's run them at 50% of their max capacity. All this is considered in our rule-based model, and we then derive a compressor sequence in discrete hourly steps. This full solution gives us a highly optimized compressor sequence, which we were not able to have before. Much more sophisticated. Using this model, our experts have actually acknowledged that they are finding entirely new strategies for running the compressors. So let's look into the building blocks of our solution. Our architecture is laid out serverless, which is not only state-of-the-art, but I think it also reflects our approach to sustainability. What you can see here is that we have implemented a hybrid solution. So we're using more than one hyperscaler, and we're using on-demand data sources. The heart of the solution is our infrastructure deployment framework, which we're using CDK for. All data, model, accounts are driven by the central CDK. We realized high security requirements and implemented VW and AWS best practices. This includes role-based access controls, a domain-based architecture, and a top-notch data management. And I want to put some focus on the data management as well as the model management and the productive use of our solution. Data sources are a number of Oracle and Microsoft databases that we host on-premise. They integrate with our production planning system and some proprietary pieces of software. For data management, we use our very own data mesh solution. The data is handled in our data management account and kept in S3 buckets. This includes data both for model training as well as for productive use. We access it via glue tables. For the data governance, we have a dedicated data governance account. It makes sure that all data is compliant with Volkswagen data management standards while being straightforward and easy to use for our users. This is actually very important because we have a lot of business users using this solution. This data architecture is the base for, I would say, almost all our use cases in commercial vehicles, and we're very proud that it's at the moment being promoted as the new DPP group standard. So whenever we have a change in the structure of our physical air compressor system, we trigger a new system, trigger a new model. And this is actually the architecture we use to generate the models. We're using SageMaker as a service as our ML solution. Model pipelines are administered and run in SageMaker pipelines. Code is located in standard AWS repositories. The models are kept in S3 buckets, and we make them available via SageMaker registry. We have all our trained models in here. Currently, it's about 30. One is productive, and the rest is for training and testing. The newest and accepted model is automatically promoted to productive use then. So it all comes together during production. A new production program is generated, and it is visible in the on-prem databases. We're event-based, so whenever we sense a change in the program, a number of steps are being triggered. We start the data collection from our on-prem databases. We prepare this data in a way that it's consumable for the model, so we have a little pre-processing job there. We then fetch and run the newest and released model. And after running the model, we have a post-processing job, which derives the optimal compressor sequence from the prognosis for the air consumption. In the end, we're using Glue to structure the data, and we visualize with our existing BI solution. During our project, we have always been fully devoted to automating this process. We also strongly believe that The ML-driven approach will be a lot more efficient and effective than any human person will ever be. For implementation, however, we opted for a step-by-step approach. We wanted to realize some quick wins, and this actually proved true. We started with our analog approach. I showed you the analog approach a little bit earlier, and we've been working like this for years, if not decades. We then focused on data. We implemented new sensors, we checked data quality, we looked at input and output data of our historical data. We learned a lot about our data. This is actually the phase when we said we feel comfortable of setting a goal of about 5% savings with our ML-driven model. We have now finished phase 2, and that's a breakthrough for us because we are now seeing the full potential of an ML solution. We're looking forward to finishing the last phase, which is a full autonomous circle of our solution. However, as we have to integrate with the compressors, with the compressor steering software, there's some upgrading going on together with the suppliers. So let's talk some data. On the right hand, you see energy use over a 3-week period. This was in 2023, so a time when we were still using the classic manual approach. Did I say right hand? On the left hand, you see 2023. On the right hand, you see the exact same calendar weeks 1 year later, in 2024. This is when we're using the ML approach. So don't focus too much on the peaks, because the peaks are usually maintenance or something that's happening out of schedule. Focus on between the peaks, because that's when we actually have our model in productive use. Even without a scale, I think you can see that the ML-based model generates a much, much better energy profile than the manual process. In fact, when we looked at this for the first couple of weeks, we realized that we had materialized a 12% better energy usage than before. I mean, this is 12% compared to the 5% that we based our business case on. So that really made our day. You don't have that very often, that you see a project that runs at 150 on top of what your goals are. So made our day back then. You might know that Poland has a very coal-depending industry. So when you generate a kilowatt hour of energy and of electricity in Poland, it's has very much coal in it. That means that if you calculate the energy savings that we have, it equals to about 1,000 tons of CO2 per year, which is a very, very high amount too. It flashed us a lot. And obviously, talking about $250,000 savings, $250,000 savings, we have a very, very strong business case here that we did not expect in this case. This is the first approach at this, so we're very proud of it. But we're not stopping here. Maya told you earlier that we have more than 114 to be precise, plants around the world. And the solution we have shown here is suitable to be used in many of those, and we are in talks to do so at the moment. Furthermore, a lot of energy in our plants is used for air ventilation, is used for heating, is used for cooling, is used for drying. So with the magnificent results we have seen in our first use case, we have just shown to you, we can start to tackle these challenges as well. So the team, Adam, Marcin, Łukasz, and Jan, have just started to adjust our solution, and we can't wait to see more great services in the future. A big thank you to the team in Poznan, to AWS, to you, Maya. Thanks for having me on stage. Back to you.
Thank you, Jörn. That was a truly inspirational example for energy reduction, and this coming from the heart of industrial manufacturing. And for me personally, great highlight to be presenting this here today, because some of you here in this room spoke about this use case with me maybe a year or two ago, and now it's actually reality. So that's really, really personally cool to see this happening. Now, our second example today comes from Amazon. And before I hand over to Marco, let's refresh on Amazon's scale and retail business. Amazon has over 1.5 million employees, and its operations run in 24 countries. Amazon's revenue amounts to circa $650 billion. Amazon's retail business delivers over 1.6 million packages per day. And for this, they use their 2,862 sites globally. Amazon leverages AWS cloud computing, storage, machine learning, and generative AI solutions, and probably many more things that I haven't thought of right now, in their operations. Marco Caserta, Senior Applied Scientist from Amazon, will now share with us how AWS helped Amazon reduce their energy consumption for their warehouses around the world. Welcome, Marco.
Thank you, Maya. The warehouse environment, with its heating, ventilation, and air conditioning system, along with the lighting as well as electric vehicles, uses up a significant amount of energy. And while we're already doing great things today, there is still a lot of room for improvement when it comes to optimizing the energy consumption at a single site on a daily level. The energy management problem at a site can be seen as a marketplace with the supplier side as well as the demand side. When we focus on the supplier side, we have different sources of energy, each one of them with a different carbon footprint. For example, we can get energy or electricity from the grid, as well as from photovoltaic panels, as well as from batteries. But on the side of the customer, we have multiple entities that use up energy in different amounts, each one of them to carry out their own operations. Well, the classical example of the demand side is all the equipment that we have in a warehouse, all these long conveyor belts that are used to transport and deliver packages to our customer. But we also have HVAC system, heating, ventilation, and air conditioning system, as well as, for example, refrigerated rooms for our cold product or fresh product at Amazon sites. So, interestingly enough, some of the entities on the customer side are non-controllables, because in reality, we can't really decide when to switch off and on our conveyor belts if we want to comply with the delivery of packages to our customers. However, other entities, like the HVAC system, the air conditioning, is a controllable entity because we can switch on and off the system while remaining within a certain comfort range. So not only this issue of controlling or not controlling, the operation at a site also entails respecting some legal requirements. For example, we need to ensure that our refrigerated rooms keep our fresh product within a pre-specified range of temperature. And something similar happens also with the air conditioning. There is a requirement that forces us to keep the internal temperature of the site within what we define a comfort range for our associates. So, having said that, what do we really want to do here? What is the problem that we are trying to study? Well, we want to find the optimal way of matching supply and demand of energy through the scheduling of these activities that are under control. More specifically, what we want to find is a solution that minimizes the total usage of energy, the carbon footprint of the entire site through the influence of the controllable element. And in reality, this is a complex multi-objective optimization problem at the heart of what is known today as the smart building problem. But it's not enough to focus on a single or individual warehouse. Our long-term vision is much broader than that. What we really want to do is to optimize energy consumption across the entire network, not just one single site. Now imagine a situation in which we have interconnected sites when we dynamically manage energy across the entire grid, balancing energy supply with energy demand for the smart grid, where renewable energy sources, like, for example, solar panels, power up the entire network, and then we use energy storage systems, like batteries, for example, efficiently to transmit the energy across the board. Well, this vision requires collaboration between multiple stakeholders as well as advanced technologies. And that's the reason why optimization and machine learning come into play in our problem. But today we're going to focus on a smaller subset of this broad vision. Today we're going to take a look at how to optimize energy consumption only for one element, the HVAC system, the air conditioning system, and only for one single site. But by itself, when we consider the HVAC system, so the air conditioning, the heating, ventilation, and air conditioning system, by itself, this component is able to absorb or use up to between 20 and 40% of the total energy consumption of a site. So the problem we are trying to solve here is how can we balance comfort, maintaining the indoor temperature of the site within a comfort range, while also minimizing the total energy consumption and therefore the carbon footprint of the site? Well, to tackle this, we developed a prescriptive model that provides optimal schedule for the HVAC system. This model integrates data from external sources, like weather forecasting information, for example, as well as data that proceeds from our sites, meters, sensors, and other devices that we use to monitor the status or the situation of the warehouse. And the goal, remember, the goal is to minimize the total energy consumption without sacrificing comfort. But at this point, we might ask, why do we need optimization in this problem? Well, consider the following example. Imagine that we are in sunny Las Vegas in summer, where we know that the daily temperature, the temperature during the day, is quite high. Let's say 100 degrees Fahrenheit, for example. But we also know that the temperature drops at night. Let's assume at 75 degrees Fahrenheit. Let's also assume that we need to maintain a comfort temperature of between 70 and 80 degrees Fahrenheit. How can we do that? How can we set up the HVAC system, the air conditioning system? Well, at least two alternatives come to mind. One would be to simply set the set point of the HVAC system, the temperature at which the HVAC system starts cooling the warehouse, at a fixed value, right below 80, let's say 78 degrees, regardless of what the weather situation is or what the status of the warehouse might be, a constant baseline solution. But then we have also another alternative. Well, exploiting, for example, variable photovoltaic production during the day, where we have a peak of production in the middle of the day because the temperatures are high, we could maybe pre-cool the site, lowering down the set point value at 70 degrees, and then once the photovoltaic energy production gets reduced later in the day, we can progressively let the site warm up. And then we intervene again, we switch the set points once more, right before reaching the threshold of 80 degrees. Well, the point here is what? That depending on the pattern of production of photovoltaic energy, depending on the outdoor weather condition, depending on the level of insulation of the site and other variables that we can take into account, the optimizer that we design will prescribe what is the best course of action. So, how does this work in practice? How can we really do it? Well, our framework uses a set of predictive models that are going into an input to a prescriptive model. Well, first, we start gathering real-time data from the building sensors and meters. And then we combine this information with weather information. And in reality, what we are doing here is we are using machine learning to capture the physical dimension, the physical dynamics of our warehouse system. With all this data at hand, we proceed with a two-step approach. The first step is the predictive part, and the second step is the prescriptive part. So predictive models are used to forecast the evolution, the physical evolution of the warehouse system. And the second stage is once we have this predictive model that captures the dynamics of the system, we embed the models into the optimization strategy, a mathematical programming device that comes up with a set of recommendations, the value of the set points of the HVAC system for a certain time horizon. Let's assume for the next 24 hours, for example. With which goal in mind? What is it we want to do? Or in reality, these set points should prescribe a course of action that minimizes the total energy consumption, the carbon footprint, while ensuring feasibility of the solution, ensuring that the temperature inside the site never goes outside of the boundaries of what we call the comfort range. Finally, once we have this prescription, we programmatically send it to our devices, to the HVAC system, and we influence the way in which the device operates. And because the system learns over time, well, this contributes to the fact that over time, while we ingest more data, our predictive as well as our prescriptive models will become better and better, more accurate. But let's have a look at a little bit more details. Let's try to zoom into this double integrated machine learning optimization approach. Well, we already said, from the predictive side, we have a number of machine learning models that are used to capture or to describe the physical reality happening at the site. More precisely, we have three predictive models. We have three machine learning models that are integrated with each other. We have a first model that we use to forecast the photovoltaic energy production for the next 24 hours. How do we do that? Well, we take some weather information, like, for example, solar irradiance, cloudiness, and other type of external information, and we feed them into a machine learning model that predicts what's going to happen in terms of photovoltaic energy production for the next 24 hours. And that's our first predictive model. Then we have a second model. The second model captures the link between a set of covariates, like external temperature, but also number of people inside a site, level of insulation, and other factors of the site to predict what's going to be the internal temperature of the site. And finally, the third model is the model that links the first two predictive models, photovoltaic energy production and internal temperature, with the total consumption of energy at a site. So with these three integrated machine learning models, we have a device that allows us to capture the physical dimension, the physical evolution of the system over the next 24 hours. But now the question is, and how do you embed machine learning model into an optimization model? Well, in reality, we have a requirement because we wanted to claim that our solution, our set of prescription, was going to be a globally optimal solution. And that limits our choice, because if you want to get a global optimal solution, we have to define a model as a linear model. So we use what we call a mixed integer linear programming model. So the question should be, from the scientific perspective, yeah, but how do you transform a machine learning model into a set of linear equations for a mathematical model? Well, to do this, we use a device that is called, or a method that is called constrained learning. In reality, what we do, we prove that we can take a machine learning model based on trees, like a decision trees, but also models a bit more sophisticated than that, like ensembles of models, random forest, XGBoosting. And we show that these models can be integrated into a linear model using a set of linear constraints. So now we have all the ingredients to come up with this optimization model, because obviously we take our predictive model for the power consumption and we put into the objective function, because after all, that's what we want to do. We want to minimize the total energy consumption. And then we take the second machine learning model, the one that forecasts the internal temperature, and we put it as a constraint of our optimization model. Because remember that the main requirement of our solution should be that we guarantee that the internal temperature at site always remains within the boundary of the comfort range. And now we are ready to go. Since we have a linear formulation, we can take any off-the-shelf solver from the mathematical programming world. Specifically at Amazon, we use Express. We run the optimization, and we get as an output a set of value, the prescription of the set points for the next 24 hours. What are the characteristics of this prescription? Well, it's globally optimal because of linearity. So there is no way of finding a solution that reduces the carbon footprint even further. And the second issue is that it's feasible in the sense that we ensure that during the entire time horizon, the temperature inside the site will always be within the comfort range. And, but there is an interesting challenge from the scientific perspective at this point. Well, because obviously the solution is optimal depending on the quality of our prediction. So in reality, we are aiming at something a bit more ambitious. The research question at this point remains that how can you get a solution that is robust? Robust in front of minor deviations of our predictive models. In other words, what if your prediction is wrong? Can you still guarantee that you have a solution that remains optimal as well as feasible? So that's exactly what we are doing now from the scientific point of view. We are trying to build a mathematical model that remains robust in front of minor deviations of our forecasting models. But now let's take a look at the architecture. How do we put all this into practice and therefore into production? Well, to present the architecture that we used, we divided into 4 main blocks. The first block is the data acquisition steps, where we ingest data from multiple heterogeneous data sources. We have a second block that deals with the optimization engine data pipeline that is gluing together all these different sources and do some data cleaning and pre-processing as well to ensure that the data is amenable to ingestion to the third block. The third block is the machine learning optimization pipeline, which is actually the core of the block, because that is where our models reside, both the predictive as well as the prescriptive models. And finally, we have the execution. Everything is cast within the framework of continuous integration, continuous deployment. Now let's have a look at the details of these 4 different blocks. Well, as we said in the first block, the data acquisition part, we integrate data coming from multiple sources. Specifically, we are talking about data that comes from our building management system through some wired sensors and meters, as well as through some wireless connection through gateways. And we put all these data sources into our Amazon S3 data lake. But we also have data that comes from third-party software. And again, even in that case, we use S3-based solution to put all the data, these heterogeneous data together. We are talking about the second block. The second block is about the data pipeline. So we have to pull together data from different sources and then make sure that we can harmonize them into a single data layer. This is ensuring that we always have the right data up to date for ingestion in our models. The core of the pipeline consists of multiple layers of AWS glue processing jobs, consolidating data coming from multiple sources. The data is also cleaned to eliminate mistakes and to transform it into a format amenable to ingestion for our machine learning models. And it's also in these steps in which we do some data quality checks using AWS Glue data quality services, a standard approach, as well as some custom-based rules, because after all, we have to keep in mind the business rules of our HVAC problems. So putting together these 2 types of approaches, we ensure that our data is up to quality for the next step. The next step being the machine learning optimization pipeline. As we said before, this is the core of the product because that is where we are launching and running our predictive as well as prescriptive models. The execution is triggered when the data pipeline, the previous step, creates a new input file, thanks to the fact that we rely on an AWS S3-based event notification. So this new input file gets into our data lake. The model starts. Our models reside on Amazon SageMaker. So we start with the inference step. The output of this step is another file. We can call it the output file that contains our optimized prescriptions. So in that file, we find what we believe, what we prescribe is going to be the best possible solution in terms of set points for our HVAC system. Periodically, we also retrain our models in the sense that we get new data, we ingest this new data into the model, and we retrain our model. And every time we retrain our model, we produce some metrics that are sent to the development team to ensure that the model doesn't drift over time. The overall pipeline is monitored using Amazon CloudWatch services that allows us to ensure fast error debugging. And finally, the last block of the architecture. The last step is about the execution. This step pushes the set points generated by the model back into the site-level controllers, and it's going to actually influence the way in which the HVAC systems are operating. This step is handled through the connection of Amazon S3 to a command executor function, which is a service that is hosted across multiple AWS services like Lambda functions, DynamoDB, as well as standard EC2 instances. The common executor, we were saying, is able to propagate the content of the output file, the set point values for the time horizon, directly to the controllers of the system, therefore influencing the way in which the HVAC system is operating. And the executor is also integrated with another portion of the S3 built-in data lakes, because it can later on in the future used for monitoring and auditing purposes of our activities. And finally, some preliminary results. So let's take a look at the results that we obtained when we applied this model on a single site on a specific day in summer. In these slides on your left side, you have the results of the predictive models. Remember the integrated predictive prescriptive approach. So how good are we when it comes to the predictive part of the story? Well, right there we are showing that we have an acceptable accuracy in terms of predicting not only energy consumption, but also the production of photovoltaic energy, which is one of the main ingredients of our approach. While on your right side, what we say is the results of the prescriptive model, the optimization model. There you see two different patterns, right? The blue line gives you the status quo, let's say, the baseline, the way in which we would operate without an optimizer. We said that the standard strategy would be to give a fixed set point that never changes during the day, no matter what the environmental condition or weather condition might be. In our example here, let's assume that we could fix the set point at 76 degrees and never change it anymore, at least for that day. The orange trajectory, though, shows you what happens if you use the optimizer in that same day. Well, as you see, we exploit information related to weather, photovoltaic energy production, and other factors, and we have a trajectory that changes over time with period of pre-cooling, probably associated to excess of production of photovoltaic energy. You reduce the set point, and then you let the site progressively warm up in coincidence with the reduction of the production of photovoltaic energy. And then we change again the behavior. So what's the difference between the two strategies, the baseline, the status quo, versus the optimized strategy? Well, we present here three metrics. Energy savings. From our preliminary study, we show that we can reduce the energy consumption, and therefore your carbon footprint, by 25%. CO2 savings. If we only applied this tool, the optimizer, to a fraction of the Amazon sites, we can reduce CO2 emission by 468 tons per year, which corresponds to planting 22,000 new trees every single year. And what about cost savings? Well, just by applying this tool to a fraction of the Amazon sites, which is a huge network, this would translate also in financial savings. We estimated savings of around $395,000 per year. But now, where do we go from here? Well, these results in itself are already significant. There is an impact there. But we can do way more if we scale these across the entire network. Now, imagine a scenario where excess of energy from one warehouse is stored and then used at another site during their peak demand, all managed by this optimization tool that continuously matches demand and supply for the entire grid. This is where we are heading. We are heading toward a solution at a network level where we constantly optimize the total energy consumption of the entire grid. And this would foster further reduction in terms of carbon footprint as well as cost and energy consumption. And we are excited to continue working with this along with AWS.
Thank you, Marco. I think that is an incredible example of thinking big and scaling together for this impact that we talked about in our industries. And thinking about the 2,862 sites, yeah, there's a lot we can still do. I'm extremely happy and proud of Volkswagen and Amazon, how they have made it their mandate to reduce CO2 emissions in their practices, and that they are leveraging AWS and machine learning for this. You have now seen examples on how they innovate and how they partner with AWS to find ways to improve the sustainability of their operations. I hope that your thoughts from the beginning of the talk, these puzzling questions, have now turned into exciting opportunities. To learn more, we'd like to encourage you to check out these resources for guidance for smart and sustainable buildings on AWS and guidance for monitoring and optimizing energy usage on AWS. And you can also read a case study on how the company Vector built a new energy platform on AWS. I would also like to invite you to join a couple more sessions here at re:Invent. We have a session on sustainable urban spaces, SUS302, and this takes place tomorrow on Wednesday at 9 a.m. And if you want to hear more about Volkswagen, there is a session on how Volkswagen's platform strategy enables production performance and quality. And this session, MFG 207, takes place on Thursday at 1 p.m. And I'd also really want to lay it on your heart to go to the CSARS forum to see the sustainability showcase. You'll discover a bunch of Legos, but also some very interesting demos on sustainability and specifically also about energy efficiency. Now, we would love to hear your thoughts and questions. So do reach out to us and come meet us. And please remember to complete the session survey. You can find this in your mobile app. We want to thank you for your attention and for your interest on this topic. And I trust that with all these resources, we have given you some inspiration for your own sustainability journey. And now, it's your turn. Thank you.
Thank you.